Last time we started and we set up the equation, but I'm gonna start from the beginning. Here's the circuit, and you are asked to find the transfer function g of s, and that is given as vc of s over vi of s. That's what we want to find, right? And we're gonna use mesh analysis for this problem. We're gonna assign the mesh current I1 of t and the second mesh current I2 of t. And from the mesh 1, say, getting into negative terminal of this voltage, therefore, we're gonna have negative V of S plus 5 times I1 of S plus for Z for this inductor is what? Ls. So L times S, 2 times S, I1 of S. I1 of S is not the only one going through this inductor, right? This is our reference current. Therefore, we need to set I1 of S minus I2 of S. Why minus? Because I1 going downward and I2 going upward. They are opposite direction. That equals to 0. And then from mesh 2, we have 10 I2 of S, starting from here, plus for Z cross to this capacitor is 1 over SC, 1 over SC, 1 over 5 I2 of S plus 2S. This time, our reference current is I sub 2. So I sub 2S minus I sub 1S equals to 0. And we want to have two equations in terms of I sub 1 and I sub 2. So I sub 1, we have 2s plus 5 I1 of s, and then minus 2s I2 of s equals v of s. From second equation, I1 negative 2s I1 of s, and I sub 2 plus, we have 10 plus 1 over s over 5. Therefore, it's going to be 5 over s, and then plus 2s. I sub 2 of s equals to 0. Put the Kramer's rule video on Canvas that I made for A Math 1. So if you're not familiar with the Kramer's rule, make sure you check out that video. But basically, if we have two equations and two unknown, so ax plus by equals to kcx plus dy equals to h. Now, we want to find x and y. So a, b, c, d, and k, h, they are all numbers. And the Kramer's rule said we can find the delta, take the coefficient of those two equations. And this is the determinant, therefore, we're going to say AD minus BC. And then we have delta 1, that is, when we have delta 1, the first column is going to be this guy. So we have K and H as a delta 1. And then B and D. Therefore, it's KD minus HB. And also that we can have delta 2 AC for the first column, and the second column gonna be K and H. And again, that's the determinant. AD minus BC. So it's this time AH minus CK. So if you have a 3 by 3, you need to go through the kind of diagonal multiplication. When we get to that problem, I show you what we need to do. But this time we have only two equations and two unknown. So it's going to be 2 by 2 matrix. Then we can find x as delta 1 over delta and y as delta 2 over delta. And if I ask you to find only y, then we don't have to go through this delta 1 over delta, right? We are not asked you to find the x. So depends on the problem. You can find, if you want, you can find both delta 1 and delta 2, x and y. But if I say only find the y, then go delta 2 over delta. So we're going to apply that in here. We're going to find the delta first. Delta equals to coefficients of these two equations. Then they are 2s plus 5, negative 2s, negative 2s. We're going to have a common denominator as an s. Then we have a 2s squared plus 10s plus 5. So AD 2s plus 5 times 2s squared plus 10s plus 5 over s and minus BC for s squared. That is 4s cubed plus 20s squared plus 10s plus 10s squared plus 50s plus 25 minus 4s cubed. So we can have the common denominator s. Then 4s cubed, gonna go away. And our delta gonna be 30s squared plus 60s plus 25 over s. So we have delta. Now we can have a delta 1 and delta 2. Now we need to have VC, right? VC is associated with I sub 2. So I'm not going to do the delta 1. We can get delta 2 directly. So delta 2, the first column is going to be the same, 2s plus 5, negative 2s. And then second column should be from the right side of the equations. Then we have a v of s and 0 AD, which is 0 minus BC plus 2s v of s. And we're going to write I sub 2 of s equals to delta 2 over delta. And I1 of s, obviously, delta 1 over delta. So delta 2, we have 2s v of s over 1 times the delta. Delta is at the denominator. Right? So it's basically 1 over delta. This is our delta, 1 over this. So I'm going to just write the reciprocal of this guy. That is s over 30s squared plus 60s plus 25. And that is 2s I2 of s over v of s equals to 2s squared over 30 s squared plus 60s plus 25. Is that our answer? No, not yet. We found the I2 of s over vs, not vc of s. So somewhere we need to find the relationship between I sub s and vc of s. How? Where? The voltage across here, right? vc of s equals I sub 2 times z, and z in the capacitor 1 over SC. From here, we say I2 of S equals S over 5 VC of S. Let's go. So we need to substitute that into our equation. Then S over 5 VC of S over V. I'm sorry, this should be VI of S equals 2S squared 30S squared plus 60S plus 25. We can multiply both sides by 5 over S to clean up. Then we have VC of S over VI of S equals 10S over 30S squared plus 60S plus 25. That is, we can multiply top and bottom by 30. 1 over 3S, S squared plus 2S plus 25 over 30. That's the answer. For the node analysis, step number 1, we need to identify the nodes. This is one node, and then the bottom node is our reference node. So we have a node 1, node 2, and the bottom one is a node 3. Node 3 is our reference. So we just have two nodes equations, basically two equations and two unknown we need. And then we're going to assign the direction of the currents. That's the step number 2. After we identify the nodes A and B or C, most likely I'm going to let this equals to C nodes because we know there's a voltage across this node as a VC. And assign the direction of the current. Really doesn't matter which way you put it in. You just need to follow the direct, the subtraction for the voltage. But typically, it is a good idea to let the directions of all those currents from top to bottom, left to the right. That's what I do all the time. So that's what I did. And then VA equals to VL equals to VR1. That's the same thing. And VB equals to VC. And then we can put the equations. So let's do this. I'm going to let this whole node as a VA. And then this is VC. Assign the direction of current. This is going into node A and then leaving to the right down. So that's the step number 2. For your solution on quiz and exam, if you don't show me this direction of the current, you are in big trouble. Without that direction, you won't be able to set up the equation correctly. The step number 3, we need to do KCL. So now we need to do KCL at node VA. So basically the KCL, what we do, entering equals to leaving. Okay, all those current entering equals to all those current leaving. If there is no current leaving, you need to let it equal to 0. So for VA, we have this guy is entering, leaving, leaving, leaving. There are 3 leaving. Entering I of S equals leaving VA over 5 for the first current downward, and then second current downward VA, V over R, V over Z. This time the Z is inductor, and we're gonna write as a 2S. And then this guy, the current going through 10 ohm resistor, there are 2 voltage sources, VA and VC. And we assign the direction of the current going from left to the right. So we need to read it from left VA minus VC, right? Left to the right. If you assign the direction of the current going from right to the left, then you need to write the equation as a VC minus VA, right? So that's why direction of the current is important. And over Z, and then Z is 10. We have VA and VC. Let's collect all the coefficients of VA. So I have 1 over 5 plus 1 over 2s plus 1 over 10. It's all of VA minus 1 over 10 VC equals I of S. The second equation, we can get KCL at VC, this node, entering VA minus VC over 10 equals to leaving VC over Z in capacitor. We say 1 over S times C, SVC over 5. And from here, VA, we have 1 over 10 VA plus VC, just make it negative 1 over 10 plus S over 5 VC equals to 0. Okay, now delta. So if we have a common denominator as 10s, we have 2s plus 5 plus s negative 1 over 10, positive 1 over 10, negative 10, 1 plus 2s. Before actually cross multiplying, I'm going to just change this 2s plus s, which is 3s. I'm going to change that to 3. And then AD 3s plus 5 over 10s. We have a minus 1 plus 2s over 10. AD minus BC 1 over 100. And if you have the common denominator as 100, I should have multiplied everything by 10. It would be much easier. Well, it's too late. So if you distribute it, negative 3s minus 6s squared minus 5 minus 10s plus s 100s. Numerator, we have a negative 6s squared. I'm going to take out negative. And then we have 13, 14, 13, 12. Okay, 13 plus 1. So we have a 12s plus 5. Okay. Again, VC is the second variable we have. We're going to find delta 2. So the first one, 3s plus 5 over 10s, 1 over 10. Second column is going to be I of s and 0. So delta 2 equals AED, which is 0, minus I of s over 10. BC of s, that's the second variable, equals delta 2 over delta. And delta 2, we have a negative I of s over 10 times 1 over delta. That is negative 100s over 6s squared plus 12s, 5. And we have minus is positive. C of s over I of s equals I have a 10s, 6s squared plus 12s plus 5. Divide top and bottom by 6. 10 over 6s, s squared plus 2s plus 5 over 6. Next, open. So don't fit it into inverting, non-inverting, any formula. I'm not going to have this simple circuit. Let's say you are asked to find the transfer function v out of s over v in of s. Now, first thing we want to do, we need to combine these two. So these are parallel and these are the series. How do you know the two components are parallel and series? If they are series, they do share what? Current. Good, good. If they are parallel, then they do share what? Voltage or two nodes, right? Top and bottom nodes. I mean, that's true. The voltage across here is the same as voltage across here. So we can say these are the parallel. That means they have the same voltage. Or they share the one node here, one node here. All the components, they have one and the other, and there's two ends. If they are connected, those two ends, they are parallel. For these two guys, current go through the same current. There's no other way, right? This is just a water pipe going in, out. All the water going through this 220 is going to be going through 0.1 microfarad. So they are series. If they are series, we just need to add, okay? So 220K plus 1 over S times 0.1 micro. And if they are parallel, we need to multiply together, divide, add them up, okay? So let's do this. For Z1, we have 100K plus 200K parallel to micro. And Z2, 100K plus 1 micro. And then we say 100K, 200K, those are the same. And for the registers, the Z is the same, but 2 micro, we should write as 1 over S C. This one should be 1 over S C. Let's work on the Z1, 100K plus. These two are the parallel. Therefore, we need to multiply 200K times 1 over 2S micro 10 to the negative 6, take to the numerator, positive 10 to the 6. And the denominator we need to add. Always, if you have two different terms at the denominator or numerator, combine them using common denominator. So we need to have a 2s, 400Ks. Then we have 100K plus, I'm gonna take the reciprocal of that. We have 200K times 10 to the 6 over 2s times numerator 2s over 400Ks plus 10 to the 6. 2s will cancel out. 100K plus 200K times 10 to the 6 over 400K plus 10 to the 6. What we can do, we can multiply top and bottom by 10 to the negative 6, 10 to the negative 6. Just for this term, then we have 100K plus. This will 10 to the 6 times 10 to the negative 6 is going to give us 1. So 200K over 400, 0.4 plus 1. There is a S missing right there, S. Finally, the Z1 now is going to be 0.4 S plus 1, 100K, 0.4 S plus 1 plus 200K. So again, I made a common denominator as 0.4 s plus 1 for these two terms. So I need to multiply 0.4 s plus 1 for the numerator. So that when we separate this, we cancel these two, we end up getting 100k. For the second one, there's, and I'm going to take this micro at the denominator to the numerator, 10 to the power of positive 6. You can have common denominator as 100k as plus 10 to the 6. So here's the key thing for ideal op-amp. There's no current going into this triangular shape in the ideal op-amp. Therefore, whatever the current going into this node, it's going to go up. Same thing for this positive terminal, negative terminal, it doesn't matter. Now, the second important thing for the ideal op-amp is if we let this as a V1, we have the same thing as a V1 for the positive terminal or negative terminal, right? They have the same voltage right after plus minus terminal. In the ideal op-amp, there's no current going in, there's no current going in. And in this case, V1 connect to the ground, so that is 0. So we have one equation that we can set it up. Entering VI, we do KCL, VI of S minus V1 of S over Z1 equals V1 of S minus V out of S over Z. I said both Z1. Which one is Z? That's Z1, this is Z2. That means this has to be Z2. This one is Z1. And we said V1, this is 0. We have, if you cross multiply, negative V out of S times Z2 equal Z1 V I of S. Now we divide both sides by VI, V out of S over VI of S equals negative Z1 over Z2. Negative Z1, 100K, 0.4 S plus 1 plus 200K over Z2. Reciprocal of that as 100K S plus 10 to the 6. We multiply 100K times 0.4 S times S plus 100K plus 200K times S over 100K. Z1, 100K, Z1, 0.4 S plus 1. Thank you. Okay, so we have 0.4, so 4K S squared plus 300K S over 40K S squared plus 100K S plus 4 times 10 to the 5S plus 10 to the 6. So this is 400K S, 40K S squared plus 500K S plus 10 to the power of 6. And the numerator, 40K S squared plus 300K S. The final answer is going to be negative S squared plus 330 over 4S. And then S squared plus 50 over 4S plus 10 to the power of 6 over 40K. So I divide top and bottom by 40K. Next, the second system that we're going to talk about is the mechanical system, translational system. And then the third one is a rotational system. And the force velocity relationship, force displacement relationship, impedance. And you can take a look at it, but we're going to use the third column. So you need to remember any spring, we're going to take as a constant K to K, just like a resistor. Dampers, we're going to have with S times whatever the dampers, and S times the frictions. And then the mass is going to be the square term. M times whatever the value mass is given, you need to turn that into square term. So watch this. Let's say we have transfer function for x of s over f of s. You will be given f of t, the direction of the force, and also transitional. So basically, we're going to pull this mass from here this way. Okay? And then we're going to look at all the forces. So look at this handout for the third column. So if we do, if you're using the differential equation, the force displacement, we end up getting something like this using all of these differential equations. And if you have more than one mass, okay, now we have 2 degrees of freedom. So what we need to do, we need to hold M2, okay, hold M2 and move M1 to the right because X1 is going that direction. So keep this, move this M1 to that side. Then all the forces is going to be here. And first case of the second scenario, this time we need to hold this M1 and M2 to the right. And we put that all. And the second case for M2 now, hold M1, move M2 to the right, and hold M2, move M to the right. Then we all have this force equations, and we put that in. Here's the equations. Okay? And x2 of s, f of s equals to, that's the transfer function. And we need to do Kramer's rule again. Easy, right? So forget about what you saw. If there are 2 masses, something like this, we're going to set up 2 equations. One for this x of 1, one for x of 2. Okay? And if there are 3, obviously they're going to be x sub 3. And then there will be only one f, the force. Now, when we look at the first equation, so we're going to write the equation for in terms of x1. x1 is where? It's m. m1. So m1 mass, we said it's associated with the s squared. So 1 times s squared, right? All right, we got. Now what we're going to do, we're going to look at all the components connect to this guy, x of 1t, which is m1. I have spring, we have a damper, we have a friction. Damper and friction, they are associated with the S, right? That's what we say. Spring, so no S's. So now there's 1 plus 1 S, and then the spring, we have a 2 and 5, which is 7, and they are all x1 of S. And then we're going to do for M2 for the second equation. Before we getting into the second equation, we need to write something in here minus the opposite force is going to happening between these two. So we're going to write something, anything in between M1 and M2, we're going to write in here. Between M1 and M2, we have 1 times S plus 5 and x2 of S equals to 0. We're going to come back to this next time. And then second equation, we're going to have m2, which is 2s squared plus, I have fraction 2 and 1. So 2 plus 1s plus the spring is only 5. That's x2 of s. And then anything in between, we said, that's the opposite direction from m1, because m1 is holding it, which is 1 times s plus 5 x1 over s. And the second equation, we have f of t that equals f of s. We'll revisit this next time.